This video will give you more information on the ANOVA assumption of normality of the errors. There are three primary ANOVA assumptions, and all of them are in relation to error, where error is determined by comparing the expected value to the observed value. And error then is determined by how far is your observed from what is expected. So all three of these primary assumptions for ANOVA really are concerned with the error that is calculated for your observed distribution. So the first one is independence. And here we want to look at, are all of these errors independent of each other? Are they independently distributed? Meaning that the error from one individual point or one group is not causing the error in another individual or another group. The second one is normality. And just like looking at normality of your continuous variables, we're doing the same here, but for the errors and the distribution of errors. So you want your normality to indicate that you have a normal curve of errors. And lastly, we have homogeneity of variance. And homogeneity of variance is really looking at the distribution of errors for each of the populations or each of the groups represented is the same, and that there's not a variation across the groups. So this way, when we look at is any particular treatment or whatever our outcome is and how that outcome is being impacted, how does that variance shift between the groups? Because that shifting of variance is what shifts the means to be able to compare those means and see if there's statistical differences. So it's important for the differences in the groups to not be from the violation of homogeneity of variance, but to actually be from a shift in the variance, thus a shift in the. So this second primary assumption of ANOVA, normality and normality of the errors, in making sure that the error distribution is normal and fits a normal curve, really has to do with again, looking at the expected versus the observed. So the expected distribution of F is expected to be positively skewed. Then your non-central distribution of F, of what you're getting from your analysis that you're conducting, should also be positively skewed. And so then when you are looking at the error, which is the difference between the expected, which is that central F distribution, and the observed, which is your non-central F distribution, you should have a normal curve of those errors. So that difference between them is the errors for each individual point. And that should be a normal curve. And so if you do not have a normal curve of the errors, it's more likely that the problem is coming from the non-central F distribution. So the F distribution that you're getting from the ANOVA analysis that you're conducting, and you'll have to reassess why your observed values or your non-central values of F in that F distribution are so different from the expected. So the easiest way to check this normality of the errors is to get the error output in SPSS or whatever program you're using, and to use a descriptive statistics option, and then be able to get a plot of these normality plots with tests. So with these normality, let me circle this here so you can see it. So this normality plots you should be able to have that option in whatever program you're using under descriptive statistics. And so you want to plot this where you want to look at the error versus the dependent variable and be able to look and see if you're getting a normal curve. So usually if you do have a violation of the assumption of normality for the errors within ANOVA, the ANOVA is going to be robust enough to overcome any of those violations of normality if you have a sufficient sample size. So if you have larger sample sizes, then you can show that you have tested for this normality of the errors, but if you find a violation in this assumption, then you're able to say that with this sufficient sample size that we have for our study, um, ANOVA is robust enough to be able to account for that violation of normality. And you can use a number of different references. There's two here to be able to support this claim that the ANOVA analysis and the results that it produces are robust enough to overcome the violations of normality with a sufficient sample size. This is just because for this normality of errors, there's really little effect on the type 1 error, which is usually what we really are concerned about. Where the type 1 error, again, is that probability of getting a false positive, where a false positive is the worst result that you can get because you're making the assumption that whatever you're doing is statistically significant when it actually isn't. And so if you have a large enough sample size, then you don't have to worry about how type 1 error is being inflated. And so this ensures that you're not losing so much power that you're unable to run the analysis. There's a number of different ways that you could deal with non-normality if that is a concern, and if you, especially if you have a smaller sample size where the analysis itself is not robust in the case of a violation. And you would deal with it in a very similar way, where if you have a variable itself not meeting the normality assumptions. So you could remove or deal with outliers. You could trim the data so that you don't have those tails that could be causing uh, a shift in your distribution so that it's not normal. And then there's also a number of different non-parametric tests. One is the Krustal-Wallis H test, and you could use these to be able to really convert your values so that you can get a normal distribution. You also can do any of the nonlinear transformations where you essentially are putting all of the distribution on a different scale to be able to make it fit a normal curve and thus be able to use it as if it is meeting this assumption of normality. The problem with all of these suggestions, not so much removing outliers, but is in the reporting and in the interpretation that you have to report any of the things that you do to try and fix a problem with normality of errors. But then also, especially if you do a transformation of some sort, now your values are not the same units as they were prior, and so trying to interpret becomes a little bit more difficult. Here are the two listed normality references for being able to say that your ANOVA is robust. And these will give you also what appropriate sample size would be to be able to say that your analysis of variance is robust in violation of normality.